All right, today we're going to talk about a catalyst. I'm going to start right out with a demonstration of a catalyst. And here I have some hydrogen peroxide. I took 30% that you get from the supply company, not 3% from the store. I diluted it to make it about 6% hydrogen peroxide, so twice as concentrated in the store. And I had this on a hot plate. I'm trying to get this sodium potassium tartrate, which is just a clear fluid, and I want it about 70 degrees. And it looks like it's sitting there. Um, Looks like it's actually right about 70 degrees right now. Now it's starting to creep up again, but 71 degrees right now. I'm going to pull that from the hot plate, and then what I'm going to do is come over and add this to this. So I'm going to add the sodium potassium tartrate and the hydrogen peroxide, and we're going to see what happens when I mix these things together. Now, because I'm adding something at 20 degrees to something at 71 degrees, the temperature goes down. But I had 100 milliliters of the stuff at 70 degrees and only 40 milliliters of the stuff at 20 degrees. So the temperature looks like it's settling between 50 and 60 degrees, okay, as I stir that around. So this is doing a chemical reaction. You should see a lot of bubbles, but I'm not seeing many. It's really, really slow, even at this high temperature. I'm thinking heating it up, the molecules are going to move faster, they're going to collide more often with more force, but it's still not going that fast. Okay, it looks like it's settled out about 57, 58 degrees. Now, what happens is maybe I'm going to add something to make it go faster, and I'm going to add a catalyst to this. I think I'm going to remove the hot plate, so from here, just to get over here. And now we're going to add the catalyst, and you can come right up here and we'll take a look. And I'm going to add some cobalt chloride. Cobalt in the +2 state has a pink color. You can see that, and I'm going to drop that in here. So I'm going to drop some amount. Now initially the temperature should drop down a little bit. I see the pink in there, and it's dropped down to about 54 degrees. I didn't add all that much stuff. And oh, I see bubbles. More bubbles. Looks like that hydrogen peroxide is breaking down. We're getting a reaction. Okay, now it's a lot more vigorous. Look at the bubbles. Look at the steam being generated. Look at that. Okay, oh, temperature's rising. We're up over 65. It's bubbling. We're approaching 70 degrees. About 72, 73 degrees. And what's going to happen to our color at the end of the experiment? Look it turned green. Now it's coming back to its original pink color. And our final temperature looks like it's about 74 degrees from about the 55 degrees before. So it started pink, it turned green, but at the end it comes back pink, and it was giving off energy, which tells us it was an exothermic reaction. Okay, so that is our experiment right there. It's cobalt chloride, our pink catalyst today. So there are some things about a catalyst that I want to talk about right here. And let's see, our catalyst, what does it do? It speeds up a reaction. Before we added the catalyst, the hydrogen peroxide and the tartrate were breaking down, but really, really slowly. Maybe perhaps more quickly if you just had it sitting in your drawer at home, but not nearly as fast as when we added the catalyst to that. How does the catalyst speed up reaction rate? It lowers the activation energy. Okay, so the reaction can follow a different path. You can look over here at a potential energy diagram. Here's the reactants, here's the products. It was an exothermic reaction. It released energy, but this would be the activation energy without a catalyst. What did we do? We lowered the activation energy by using a catalyst. So essentially it put a tunnel through this mountain and made it a lot easier to get from reactants to products. Okay, the old path is still available, so if some molecules had enough energy, they'd still be able to get up over this hill. Technically, it adds at least one step to the reaction mechanism. Usually we don't show this in a drawing, but we could maybe draw two small hills right here, making this. Typically we just simplify it and show one level going over like that, and that's fine for what we're going to be doing. And then probably a really, really important thing is a catalyst really doesn't get used up because it gets regenerated in the last step of an experiment or in the last step of the reaction mechanism. So you start with it and you end with it, and it appears like it hasn't been used. So we started with the pink, we ended with the pink, it appears like it hasn't been used in that process. Just a little bit more with that is this isn't the reaction mechanism, it's talking more about the cobalt catalyst. And what happened, cobalt in a +2 state is pink, but it turns to a +3 state by losing an electron, which is green. And that's where it exists through most of the experiment. But at the end, it gains an electron, the cobalt +3, and it turns back to pink, and that's the last step. So when this cobalt loses an electron here, it allows the hydrogen peroxide to gain an electron. And when this gains an electron, it allows the tartrate to lose an electron, so it made the exchange of electrons between the peroxide and between, or the hydrogen peroxide and between the tartrate happen much more quickly at a lower energy. Okay, so just a couple things here. We had an exothermic reaction, so we go from a higher to a lower thing. Energy, that was the steam being generated. It went faster because we provided a lower energy pathway, which was the catalyst, which lowered the activation energy. But notice with the catalyst, our starting point and ending point's the same. We just have a lower energy pathway right there. Okay, I'm just going to summarize one other thing because we've talked about some other factors affecting reaction rate. I'll focus on three: concentration, temperature, and a catalyst. How would changing concentration affect the reaction rate? Well, if you increase concentration of something and that reactant is part of the rate determining step, what's going to happen is you're going to get more collisions, and more collisions should lead to more collisions that exceed the activation energy and a faster reaction. So looking at that diagram, does it affect this diagram? No. It's kind of like having a race from here to get up over the hill, like, I don't know, a Ninja Warrior or an Ultimate Beastmaster type of event where you have to climb over this rugged hill right here. And instead of having 100 participants, you might have 1,000, and just because you have more are likely to get up and over the hill. What if I raise the temperature? What would that do? That doesn't change the number, it doesn't change the course, it changes how much energy each has. So maybe I'm giving each contestant a bunch of rock stars before they go, or some PEDs or something, and the ones who would have only gotten here now get to here, the ones who got here get to here, and the ones who are here now get over the hill. So that would lead to a faster reaction. More energy, higher impact collisions, more collisions, so more collisions that exceed the activation energy. And the last piece is, how would adding a catalyst affect things? It doesn't speed up the molecules. It doesn't mean there's more molecules. It actually changes the course. It provides a lower energy pathway for that reaction to occur. It changes the reaction mechanism, adds at least one step, making it essentially easier for it to achieve its activation energy because the activation energy is lower. And that's what's happening right here.